Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled ChemClay model, and it is going to provide you a broad overview of ChemClay model and also the work equations for this model. I'm going to give you an overview of what I'm covering in today's video. First at all, we will have a look at some fundamentals of the ChemClay model, then move on to the mathematical derivations for this model, then wrap up with conclusions. A most important development in the campaign to predict and control the stress-strain behavior of soil was the development at Cambridge of a group of plasticity models, introducing Schofield and Ross' most philosophical and useful book, Critical State Soil Mechanics. It will transpire that uniform dense soils can remain quasi-elastic right up into the viscosity of the stress condition tau equal to sigma dash times tangent phi c dash. However, the focus of the Cambridge models is the behavior of loose soils which yield and become inelastic, like point Y as shown in right-hand side figure, at much smaller angles of inclination of stress. Perhaps even more significant, the plasticity models draw a comprehensive picture of compression, elasticity, yield, friction, and cohesion, which helps in the enormous task of gaining a perspective over the whole geography of soil mechanics. Now we will start to introduce how to derive the work equations for ChemClay to describe the behavior of soils. Schofield and Ross derived ChemClay from work equations applied to a triaxial test sample suffering very slow change increases in stress delta Q on Q and delta P dash on P dash, where Q is the deviatoric stress and P dash the average effective stress. Associated with deviatoric stress component Q is the shear strain epsilon s of the 1 to 3 plane, while the strain associated with the spherical stress component P dash is the volumetric strain epsilon v. The first step is to establish the work done by the stresses at the boundary of an element which can strain. Consider an elementary cube of soil of unit side which is aligned along the principal axis so that the only effective stresses acting on it are the principal stress sigma 1 dash, sigma 2 dash, sigma 3 dash. Suppose that the one axis of the cube shortens by a small strain epsilon 1. The stress sigma 1 dash acting on unit area moves the distance epsilon 1 times unit length. The work done per unit volume by the sigma 1 dash stresses is therefore the force multiplied by the distance, sigma 1 dash times epsilon 1. If the two axes shortens by epsilon 2, then the work done by the sigma 2 dash stresses will be sigma 2 dash times epsilon 2, while that in the 3 direction will similarly be sigma 3 dash times epsilon 3. We have assumed that the effective stresses are constant, and that no excess pore water pressures are caused. We have also assumed that the effect of the small strains on the areas and volume is negligible. The total work done per unit volume by the boundary stresses shows here. We now require to translate the cubic system into our triaxial system with the 2 and 3 directions equivalent, so that we have this equation. Following the principle of multiplying stresses by their corresponding strains, we shall attempt to translate W into the Q P dash system. Here, we calculate Q times epsilon s and P dash times epsilon v, so that by inspection, we obtain this W equation. In order to eliminate the inconvenient 2/3 factor which has appeared, we shall adopt a new strain component epsilon Q associated with the deviatoric stress Q in a triaxial test, so that we can write this simply W equation, which is the work done by the environment on a straining triaxial element of unit volume. Now consider the effects of a small increase in stress delta Q in Q and delta P dash in P dash, supposing that they cause small changes in strain delta epsilon q in epsilon q and delta epsilon v in epsilon v. The average stresses during the increase were q plus half of delta q and p dash plus half of delta p dash, and the resulting strengths were delta epsilon q and delta epsilon v. So the increment of work done by the environment on the sample was here. We can omit the higher order terms so that the delta W equation shows here, delta W equal to delta W basic. Where has the work gone? The environment has fed in work delta W to the element. The element must have stored some energy and dissipated some energy as heat. Elastic systems store energy, various plastic systems dissipate it. In order to make progress, it is necessary to come to a fairly simple and crude decision regarding the storage and dissipation of energy in the sample. In ChemClay, the decision Schofield and Ross made was that all deviatoric energy is dissipated, all volumetric energy is stored along kappa lines in such as this figure, and dissipated when the soil state changes kappa lines. Considering the E versus ln E P' diagram, an arbitrary movement A to Q will be thought of as part plastic A to P and part elastic P to Q. Suppose that APQ are quite close, so that the void ratio E changes only infinitesimally. The total volumetric strain delta epsilon V shows here. Part of this is elastic and recoverable delta epsilon V elastic, while the remainder is plastic and dissipative delta epsilon V plastic. Considering just the plastic component, you will see from this figure that EA minus EP equal to minus delta epsilon kappa, so that the plastic volumetric strain shows here, which we might write as delta epsilon kappa, and the plastic volumetric work must therefore be this equation. We can now deduce the magnitude of the plastic work which is fed into the element and presumably dissipated. This equation represented that part of the work done by the stresses at boundaries, which was not stored. We will assume that this work has been dissipated in friction and that the form of the dissipation equation shows here. We presume that it must have been dissipated, and this equation invokes a dissipation equation which contains a friction constant m for the soil, the average effective stress P' crunching the grains together, the magnitude of the change of shape of the element, put inside a modular sign so that work is always dissipated, even if the element gets longer and narrower, delta epsilon q less than 0. By merging the two equations, we obtain the basic plastic work equation for ChemClay and shows here. Considering compression, delta epsilon q larger than 0, so we obtain this equation. This equation represents the following conditions. The first one is elastic. The state of the soil will reside on a single kappa line so that delta epsilon kappa equal to 0. Furthermore, delta epsilon q equal to 0, since the deviatoric strain in ChemClay is a purely plastic phenomenon. Q is indeterminate. The second is plastic contraction. Delta E less than 0, so delta epsilon kappa larger than 0. Therefore, Q less than P' times M. The third is plastic dilation. Delta E larger than 0, so delta epsilon kappa less than 0. Therefore, Q larger than P' times M. The fourth is plastic deformation at constant volume with unlimited shear strength delta E equal to 0 and delta P' equal to 0. So delta epsilon kappa equal to 0 and delta epsilon q to infinite. Therefore, Q equal to P' times M at a critical state. The Q versus P' diagram shows in this figure. This figure also contains an elastic zone which has arbitrarily been drawn fairly close to the origin on the presumption that there are some small stresses which elicit elastic responses in a fairly dense soil. The second major step in the derivation of ChemClay is to invoke Drucker's concept of stable yielding on the elastoplastic boundary, which plasticians often call yield surface. In this delta W equation, the last term represented the work done by the probe, delta Q, delta P' itself. Consider a point A on the yield surface in this figure. If a small probe causes the stress to move towards E in the elastic zone, the only response will be movement along a kappa line. We demand that the soil remains elastic, so E kappa equal to constant, and delta epsilon kappa equal to 0. Therefore, for any inward probe from A, since delta epsilon Q equal to epsilon kappa equal to 0, it follows that there is no plastic work done by the probe, and we have this equation. If the small probe causes the stress to move towards P in the plastic zone, then we must expect that delta epsilon Q and epsilon kappa are equal to 0. If the probe actually does plastic work on the element, then Drucker described the yield as stable, so that we have this equation. Finally, consider a probe AY which just travels along the tangent to the yield surface. A well-behaved plastic material would then obey this equation. This would imply that a probe which only just causes yield would itself do no plastic work on the element, just as would a probe which just misses causing yield. This equation can be rewritten as this expression, which fixes the strain increments in relation to the yield surface, as demonstrated in this figure, and gives rise to the description of this equation as the normality condition. Now we know the ChemClay plastic work equation and the normality equation. Next, we will introduce how they work. Checking the work equation in compression. With the normality equation, the strain vector can be determined to give this equation. To describe in calculus the yield surface in terms of its position and its gradient. Using the substitution eta equal to Q over P dash, we derive these equations. Now, one point on the yield surface must be a critical state QC equal to M times PC dash. This fixes the constant as 1 plus ln PC dash. The equation of the yield surface reduces to this equation, which is depicted in this figure. One of the most powerful aspects of the ChemClay model is that it predicts that the extent of a kappa line is limited. There is a pressure PV', which, if applied, causes plastic contraction even in the absence of deviatoric stress. We are already acquainted with the steep lambda line, which describes plastic compression after the pre-consideration pressure PV' has been exceeded. Substituting Q equal to 0 into the yield surface equation, we obtain this expression. ChemClay has predicted that the critical effective pressure is reached when the over-consolidation ratio PV' over P' is just less than 3. Ratios much less than 3 will indicate loose states. Ratios much greater than 3 will indicate dense states. Now suppose that the critical states are known to lie on the line, and we have this equation. For each critical state, EC PC', there is a point of plastic compression of volume, EV PV', a fixed distance out along a kappa line, which means this relationship. But we know ln PV' minus ln PC' equal to 1, so that after some derivations, we obtain this EV equation. This is the equation of a line of spherical plastic compression running parallel to the assumed logarithmic critical state line. The predicted Q, P', E diagrams appear in this figure. Every kappa line is limited in extent by the plastic spherical compression line, and above each kappa line is shown one of the geometrically identical family of leaf-shaped yield curves, as shown in this equation, which are scaled in proportion to PC', which is at the intercept between the kappa line and the critical state line. From conclusions, what we learned? The ChemClay model is an elastic plastic strain hardening model that is based on critical state theory and the basic assumption that there is a logarithmic relationship between the mean stress and the void ratio. This model describes three important aspects of soil behavior: strength, compression, or dilatancy, the volume change that occurs with shearing, and the critical state at which soil elements can experience unlimited distortion without any changes in stress or volume. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.